Hi everyone, my name is Katie Tillman and I'm a College of San Mateo alum and currently attending Sonoma State University, where I'm majoring in astrophysics and minoring in math. This summer I had the opportunity to work with Professor Dimitri Mouet and Dan Echeverry of the Exoplanet Technology Lab at Caltech, and this presentation is about Vortex fiber nulling. For a quick overview of the presentation, we'll get some background info of similar techniques and long-term goals for this project, along with an explanation of how our design is different from others. And the methods and approach slide will provide insight to the simulation work I've done and expand on previously completed parts of the project as well. This will then lead into the results of those simulations, and leading away from simulated work, the Keck Planet Imager and Characterizer, or KPIC, slide will introduce the in-lab hands-on work that I was able to do as well. Vortex fiber nulling is a new interferometric technique for characterizing exoplanets at small angular separations from their host stars. Interferometry is a technique in which waves are superimposed to cause interference, which we then use to extract information. VFN is particularly worthwhile because it allows exoplanet characterization at or within the theoretical diffraction limit of telescopes, a factor 2 to 3 times better than conventional coronagraphic techniques. The diffraction limit of a telescope is the minimum angular separation of two sources, like a planet and a star, that can be distinguished by the telescope, and this is constricted by the diameter of the telescope. Now, traditional fiber nulling interferometers use sub-apertures, while VFN has the advantage of using the entire telescope aperture. In other words, VFN is able to use the entire diameter of the light collecting region instead of making smaller sub-regions. And by using vortex fiber nulling, we can differentiate light from a host star and light coming from a planet orbiting it. To do this, we use something similar to conventional coronagraphic methods. The top right graphic shows how one of these conventional coronagraph works. We can see that the coronagraph mask is placed within the beam of light that is coming from the star system. And once the mask is in place, a lot of that starlight is blocked, with the remaining light being focused to the outer edges. A Leo stop is then added to block most of the remaining starlight, and as a result, the starlight is suppressed to the point where the planet is now visible since it's not behind the star's glare. This light will be used to characterize the atmospheric composition of these planets using spectroscopy. And in this process, the planet light will be input through a spectrometer, which will measure the properties of light over a portion of the electromagnetic spectrum, and the output will be something similar to the image on the bottom right. This technique serves to search for key molecules known as biosignatures in the planet's atmosphere, such as methane, water, carbon dioxide, and others. And these results could allow for us to characterize potentially habitable Earth-like exoplanets. Now to look at VFN's specific design and see how the light comes through the system. We can see that the starlight and planet light are coming in and passing through the vortex mask at different angles. This is shown in red for the star and blue for the planet. Now the vortex, as used in VFN, is distinct from how a typical coronagraph mask is used, compared to the graphic in the last slide. And in that graphic, the starlight was physically blocked by the coronagraph, while in VFN we let the light get to the final imaging plane. It will come to a focus on the center of the line within the gray block on the right. Now remember, the coronagraph mask and Leo stop work together to completely block the starlight that's coming through. Even though our vortex mask doesn't block the light, the starlight in red lands exactly on the center of the fiber, making it symmetric in a way that the star's phase actually cancels out, meaning that we don't get any of that starlight in through the fiber. Now looking at the blue line for the planet light, we see that it lands off-center on the fiber, making it asymmetric such that the light will get in. My project for the summer was to see what kinds of planets VFN can detect, and more specifically create a target list of stars for when we start observing with VFN next year. To do this, I started with a previously generated list of promising targets for the VFN mode of KPIC. I then expanded on an existing simulation code that now utilizes actual star parameters such as mass, diameter, and temperature. Looking at the graph on the left, we see that there is separation on the x-axis and mass on the y-axis. This graph directly shows us the mass and separation for a companion object, which could be a planet. Data from the European Space Agency's Gaia mission was taken to create these graphs for stars whose accelerations are not in a straight line. A non-linearly accelerating star could mean that there is a companion object, like a planet, near the star that causes that motion. Graphs like these were made for each of the 67 target stars to try to explain their accelerations. So to understand this graph a little bit better, if we look at a separation of 70 milliarcseconds, Gaia data predicts that we will have a planet with a mass of 11 Jupiter masses. This means that for this specific target star, unfortunately, I'm not allowed to give the names of these stars, so all of them will just be referenced as target star. But this means that for this specific target star that has a nonlinear acceleration, if we look about 70 milliarcseconds away from the star, we would expect to see a planet of 11 Jupiter masses. This entire graph shows the probable separations and masses for a companion planet, if a planet is in fact what is causing the star's acceleration. Now the graph on the right shows the outcome of one target star that has been run through the simulation code. By looking at the white contour lines, we can clearly see that this would be highly detectable for K-VFN, since the majority of the graph is above the SNR ratio line of 5.0. Now for this specific target star, this graph shows us that we should be able to detect a companion planet of at least 3 Jupiter masses and at a separation of up to 80 milliarcseconds. Now without even looking at the x and y axes, we can see by looking at the contour lines that most of this graph is above the 5.0 line, making this a promising target star for K-VFN. And now combining those two separate plots, we created final sensitivity grids for each of our 67 target stars. Now overlaid, we can more clearly see with what mass and at what separation a planet would likely be at orbiting our host star. The parameters on the side that are in bold were taken from online catalogs. For every single star system in our target list, our code goes online to pull the information measured and contained in the TESS input catalog and the 2 mass all-sky catalog of point sources. The parameters for the companion object were chosen using evolutionary models that predict how a planet evolves over time, using the host star's age and the planet's mass. And the final parameters on the bottom we are assuming for our observations. To relate the parameters on the bottom to the figure on the right, we are assuming that we can observe the planet for 10 hours, and we assume that we can remove the systematics in our observation to within 0.1%. In other words, we can remove the Earth's own atmosphere, since we will be observing from Earth, from our detected spectrum to 0.1%. And to highlight from the previous slide, the purple region is the most probable planet mass as predicted by Gaia astrometry data, and the background in shades of blue and green is how detectable that planet would be with anything above an SNR of 5.0 considered detectable. So to look at that contour line of 5.0 again, you can see that this star and possible companion planet, that it's a member of our actual target list, would be detectable with K-VFN as early as the end of next year. As long as that acceleration seen by Gaia is being caused by a real companion, and as long as the planet exists within a separation of about 100 milliarcseconds. Now within this range of 100 milliarcseconds, we see that this planet is above 5.0, which means that it's detectable, but it is also above 100, which means that it's highly detectable. And with these highly detectable planets, we can do advanced spectroscopic methods to determine things like this planet's spin and weather, if it has clouds, how quickly the clouds are moving, and what the clouds are made of, essentially providing a weather forecast for this exoplanet. Now, most current coronagraphic systems are limited to looking at separations beyond 100 milliarcseconds, so they wouldn't be able to detect this planet if it existed in this region. But the region to the left of the 100 milliarcsecond yellow line is a region that only K-VFN and a few other techniques currently being developed will be able to detect. But I'm happy to say that K-VFN might be the first one to be able to look at these regions on sky. And toward the end of my summer research, I actually got to work on the physical K-PIC Phase 2 instrument with the whole plate imaged at the center. And a very simple run-through of this plate is that the yellow cord is the light source being used in the optics lab. The light travels through the system, hitting each of those little mirrors that have been perfectly adjusted for maximum light throughput. and that light is collimated and brought to focuses throughout the entire instrument and finally lands on the camera attached to the back. By performing characterization tests, we can gain insight on how the moving parts of the plate will behave over time and after being told to move by our computer programs. For the first test I performed, I moved the tip tilt mirror, shown on the left image, to its maximum point and moved it down incrementally to see if it moves linearly or has some erratic movement within that range. This mirror moves exactly as its name describes. It tips and it tilts, which changes the direction of the light going through the system. The image on the right shows the retractable fiber stage with the yellow optical fiber in place. This stage can retract horizontally to move the light source in and out of the entire optical system. And the tests I performed on this stage were to move the stage in and out of the system and see the relative motion in the X and Y direction with respect to the original image. The second test on this was to physically remove the optical fiber and replace it, which will tell us if and how the focus is changing each time it is removed. In conclusion, the VFN mode of the Keck Planet Imager and Characterizer will be able to look at exoplanets with a small angular separation from their host star, much smaller than any existing chronographic techniques. A promising target list for the instrument's first light can be made using the sensitivity grids that tell us the mass and at what separation a planet would need to be at in order to be detectable with KPIC VFN. Future steps for the project include creating a list of stellar binaries given parameters for VFN detectability, using the Washington Double Star Catalog, and finishing the data analysis for the tip-tilt mirror. I recently co-authored a paper on VFN, which is available on the SPIE Digital Library. You can either search my name or the title of the paper, which is Broadband Vortex Fiber Nulling, High Dispersion Exoplanet Science at the Diffraction Limit. I'd like to thank Professor Dimitri Mouet and Dan Echeverry for their insight and guidance throughout the summer. I'd also like to thank the funders of the Joseph Rhodes Junior Wave Fellowship, Jim and Marcy Beck, for their support and interest in scientific development. And finally, I'd like to thank you all for watching this presentation today. Please email me with any questions or comments you may have. Thank you.